actually, it contains some new ideas, so I will try not to be too fast. I mean, so please interrupt if you feel you need more comments. So there's another story which is also quite useful in many situations. So what's that about? And I'm going to explain the setup from two different viewpoints which are equivalent, I mean, using exactly the same notation. So what is the viewpoint A? Assume we have a filtration, so that's not about SDEs. I mean, so SDEs are over. So, well, though we will have an example. I mean, that's something different. So assume, as usual, we have some filtration, and there is stochastic calculus on this filtration. So assume we have some martingale, local martingale. Maybe local martingale. Should I say started from 0? Probably yes. And let dt be the exponential martingale. This empty. So this is again a martingale local martingale started with the value 1 now. And assume that we know that we also have an input, that it is actually a true martingale. But we have some boundedness that guarantees, okay, this is a true martingale. So here is a remark, first remark. There is a simple sufficient condition, which is called Novikov's theorem. Which says that if the expected value of exponential of 1/2 MMT is finite, then we're okay. You can interpret it saying that, okay, if we do not, do not subtract too much here, then it's fine. I mean, if it holds up to time t, then this is a true martingale up to time t. But you can just assume that you have some other boundedness that guarantees you this condition. Or, okay, there are weaker criteria. Okay, now let this is conceptual. And so I'm going to be as slowly as I can. So we have a probability measure, which is denoted by dp. Let me now introduce another probability measure on the same probability space. Let us define another probability measure. dq, which is p reweighted by the factor dt. So for simplicity, let us think about t capital being finite. I mean, everything stops in finite time. It's better to work with, I mean, you can do this on the whole half line, but let us assume everything is finite. Otherwise, you need some theorems that martingales have limiting values, so almost surely, etc. Okay, so why this is still a probability measure? Just because this is a martingale, right? The total expectation of dt is 1. So I just reweighted everything using these trajectories. Okay, and this is positive because this is exponential. Okay, this is setup A. Setup B is, as I said, in a sense, exactly the same, but you can do it other way around. So you can do it the following way. Assume that we start with some another probability measure. Let dq be a proba measure such that on ft capital, this is absolutely continuous with respect to dp. I'm not interested in anything that happens after, I mean, how to say, I mean, above the sigma algebra ft. Okay, denote, in this case, is denote dt to be a Radon-Nikodym derivative of what? Of dp over of dq over dft. Well, it is defined maybe only up to measure 0. I mean, there are some technicalities. But what you can say is that exactly from this definition, so it follows that dt is a martingale. So what I'm explaining you is exactly the same picture. So now you just say, okay, here I can think about this, introducing this new measure in a progressive manner. Like at the very beginning, I just do not know nothing. So I mean, at f naught, this is just the same. Then my paths evolved for a while, and I have some distribution on these guys, right? Then I compute this weight, and at this time, I just reweight the probabilities by dt. Then I compute, I mean, I evolved for more time, and I refine my reweighting. Okay? Yeah, well, that's not what I wanted to say. Yes. This is dp restricted on ft. Okay? So this is a martingale, and then I can say, okay, let me try to find mt such that this holds. It's a martingale, positive. Let mt, well, okay, be such that it holds. In fact, you can write it in an explicit manner like that. So that this is some computation with the eta formula. A small remark is that, of course, this MT is unique. I mean, if you ask this condition to be true, then you basically ask that. And this is a decomposition of log dt into a martingale part and the bounded variation part, right? This decomposition is unique. What is slightly suspicious is that this part is exactly the quadratic variation of that, but this is a consequence of the fact that d was a martingale. I mean, so it must be some relation, and this is exactly the relation. Okay? This is setup B. So the message here is that this is exactly the same picture, just viewed from two different positions. If it's easier for you, you can just take the first one. But somehow the second one is slightly more conceptual, what's going on, and we will see this in examples. Now there is a theorem. And in fact, this is a fairly easy computation. So it says that let C be a local martingale. Now I put here with respect to dp. Okay, we just had all martingales with respect to dp. In the second line, we are going to have martingales with respect to dp. Then this is a local martingale respect. Well, okay, it holds, both with local and without. So what is the claim? Yet again, we now have two measures on the probability space. Maybe it's slightly easier to think about just measures on trajectories of something. They are absolutely continuous with respect to each other. So this is the same set of trajectories, just with different probabilities. And now what I'm saying is that there is a simple rule to track what happens with martingales with respect to the first measure and with respect to the second. And the rule says, okay, you just add or subtract the bracket with the underline m. And the very first remark is that, in fact, dp and dq play equivalent roles. So you can go back. You can, other way around, start with dq. With dq weighted by dt minus 1. And then note that dt minus 1 is exponential of mt, say tilde minus 1/2 e tilde m tilde t, where m tilde t by definition is mt plus quadratic variation. And then probably it holds, right? So we have minus mt plus quadratic variation minus 1/2 quadratic variation. So this is exactly inverse again, and this is a martingale with respect to dq. This is a part of the theorem. Okay, now the sign is reversed. So in particular, I can apply the theorem to n being equal to m. This gives me some other martingale, which is denoted by m tilde here, up to a sign. Okay, so of course it must be this case. So there is no actual difference between dp and dq in this setup. So if we can go one way, then we should be able to go other way around, and this is exactly how it works. Okay, just to make it clear, and to make you feeling better with this with this transform. So this is exactly, in particular, what must happen with M if it has some chance to be true. Okay. So this is the statement, and the proof, as I already said, is easy. Let me try to say it. Well, maybe without all the technical details, but that's really very, very standard. I mean, just an essential fact is here. So claim. What does it mean to be a martingale with respect to the new measure? Is martingale with respect to dq if and only if dt lt is a martingale with respect to dp. I'm going to write a formal proof, but let me first insist that, okay, it must be something of this sort, right? Because what is the difference between dq and dp? It's just reweighting, I mean, just put an additional Radon-Nikodym derivative in front. So it's basically exactly the factor that must appear in the expectations. Okay, so the proof of this claim, okay, let Z be bounded Fs measurable, then what I must check for the expectations with respect to Q, I'm going to put Q here. So I must check that this well, yes, that this is equal to LSZ there. So what I know is that this is the expectation with respect to P dt capital. This is just definition of dq. Then I know by the martingale property of D that this is the expectation of dt LTZ, since dt is a martingale. Right? Because this is measurable with respect to ft, so I can just put t here. And well, the only question is if it's true that this is ds LSZ, which exactly by the same argument is equal to expectation with respect to Q LS. I mean, the question if these two gentlemen are equal is exactly the question if those two gentlemen are equal. And this states that LT is a martingale with respect to Q, and this states that DL is a martingale with respect to P. Just okay. So I mean, the proof is really extremely simple and straightforward, but in fact, you know, it's very, very natural. When you reweight the probability measured by something to check that something else is a martingale is nothing but just to check that being multiplied by this dt, it was a martingale. Okay, good. And once we know this, this is just a computation, so let me write it, say here, you know, to keep something visible on that blackboard. So now this is just a computation. By either companies. So how does it go? Okay, what is d dt lt? Okay. I should check that this is a martingale. Let me first write this term because dt is a martingale, so this produces me a martingale part. So then I should write dt by dl. So what's that? dt by dn minus dt bracket nm. I wrote the second term. And then there is the last term, which is the bracket between d and l. So the bracket of d and l. d L and okay, in L this is the martingale part. This is bounded variation, so this is dm. Okay. This is d. And all that is martingale part. So the only question is if this cancels with that. And this must be easy. Why? Because I know what is the link between M and D. It's here. So I know that this is actually D and D over DT. Just because of that. Was it possible to follow? Nope. Well, let me drink and see. So this is the first term in data form, LDD. These two are DDL. Okay, this definition of L. The last term is, okay, the last term of the eta form. These are martingales because D and, I mean, the stochastic integrals corresponding to this notation are martingales because D and N are martingales. And it's whatever we put here, this is still a local martingale. So the only question if this cancels with that, okay, it's simple computation because we know that M is a stochastic integral with respect to D of sums. Okay, this exactly cancels. Again, the message is that it cannot be hard. I mean, if it works, then it should be, a really straightforward way to check. And here is the way. Okay, good. So now I wouldn't like to erase the setup because this is of much more importance compared to the proof. I mean, just you had a chance to follow. So let us think, what does it tell us? Basically, this is a very, very conceptual thing. So it says that, okay, there are two procedures. The first procedure is, well, it takes whatever martingale we have, M. So M should be thought about as fixed. I mean, everything that's set up is fixed. It takes a martingale and it subtracts a bounded variation process. Right? This is not a martingale, of course, anymore with respect to D. And the second procedure says, okay, I just introduce a new measure, dq, instead of dp. And these procedures have the same effect. So let us see this in examples. I mean, how it works. So the first is weak solutions to SDs. And in this example, this is an SDE of the simplest possible form. So, okay, it's going to be an SDE dxt is d beta t, right? And this is the same as it was in the first half. I mean, it's going to be beta, not b. Some auxiliary Brownian motion plus some term. Okay. What you can have in mind, for instance, is like Bessel equation. Maybe Bessel is not that good because there is a blow up here. Okay, let's see how it works. So let B let it be 0t is, say, just bounded, measurable bounded function. Measurable and bounded. So I do not assume any smoothness there. I mean, just sums. Okay. Take MT. This is a generalization of the construction we had before the break. So take the stochastic integral of this form, BS, dBs, where B is a one-dimensional Brownian motion. So I start with the one-dimensional Brownian motion B. I take the filtration generated by this B, and then I just consider the stochastic integral. Okay. Right now there is nothing to do with Girsanov theorem. Okay, and denote dt as we should. Okay, as I said, there are some issues with integrability. Maybe let me just relax even this assumption with boundedness. So let us assume instead of boundedness is that we have such a measurand G, Gs, which depends only on S, with G in L2. If you wish, just think about bounded functions.
B is from 0t times something. Something this way.
Thanks. Thanks. Yes. Thanks. I mean, the time is on the segment, the space is R. And what I assume is that the function is bounded in space at each particular time. And in time, okay, the measurand is in L2. If this holds, then you can easily check that this condition holds. Just because the quadratic variation cannot exceed the L2 norm of G. So in particular, means is a true martingale. But again, this is a sort of a technical condition, which is of importance, but not the most important thing here. Okay, and now what do we know? I'm going to apply this theorem to this D and M. So D and M are exactly as in this setup. And as a martingale N, I'm going to take D, BT. Okay? Apply Girsanov with, it was N, which is BT. And it means, well, what we have is that, okay, this BT minus quadratic variation. What is the quadratic variation? What is the bracket? The bracket is, okay, this is the bracket of this with b minus integral b s s ds. The bracket. So this is a martingale with respect to dq, which is dt. Okay. Okay. So this is general philosophy. There is a way to change my probability measure so that this guy is a martingale. Okay. Note that we have a martingale, and I'm wondering what is the quadratic variation of this martingale. The quadratic variation, it is defined in a way which does not refer to the particular values of the probability measure, right? It's just the limit of increments squared. So this is a bounded variation process. Okay, what I'm saying is that beta t, not that quadratic variation of beta is bbt is t. Just because, okay, because this object is not dependent on if we take dp or dq or whatever. Okay, so we have a local martingale. So we have a local martingale with variation in t. It means this is a Brownian motion with respect to the new measure. It's one-dimensional. Okay, everything is one-dimensional. It's a Brownian motion with respect to the key. Right? So the probability space as the space is the same, but the measure is changed. And the filtration is the same, but the measure is changed. Okay? It's a Brownian motion with respect to dq up to time t capital. Okay, but then I'm just saying that, okay, this b, actually it solves stochastic differential equation, which is written exactly here. So just here. In the probability space equipped with the measure Q. Okay. What is the most important consequence of this consideration? if I just think about solutions to these SDEs as random variables with values in say, in continuous functions, measures. Say that are absolutely continuous with respect to each other. In particular, with respect to the Brownian motion itself. Right, because this is exactly, I mean, what all this story is about. I mean, we have two measures, dp and dq, which are mutually absolutely continuous with respect to each other. And what we see is that the Brownian motion with respect to the one of them is a solution to SDE, to this SDE with respect to another. So again, this is a very, very general statement. So it says that the only influence of this drift term is basically it reduces to making some trajectories more probable than others. And so you still have the same set of trajectories. So in particular, all the path properties like Hölder exponent 1/2, all the properties of the set of zeros, etc., and so on and so forth, they are all the same. So the only thing you do is actually changing the probability measure. Okay, so good. In particular, so let me add it here. The same applies, for instance, to Bessel processes. Up to time they hit whatever level that. So of course you cannot say that the Bessel process has the same distribution as the Bessel process of small dimension has the same distribution as Brownian motion, because once it hits zero, it stays zero for forever. But still, if you just make a sort of a truncation in the same flavor as we did, I mean that's the same. I mean in the bulk they're exactly the same trajectories. So that's of importance for all the courses in the CLE you are going to have, and for many other things. Okay. Good. Now, still there are two more examples which basically are particular cases of this example. So example 2. Let us think this is simpler. I mean, this is just a reduction of example 1 to in a sort of a stupid situation. Let us think about B, about the case when B does not depend on the space argument. B as x is just a function of the time itself. Okay. So in this case, what is the correspondence we have? What is the correspondence that we have? This function is deterministic, right? It does not depend. I mean, here is the most important equation. So the second term is deterministic. Okay. So BT is just BT minus some HT, where H is the primitive of G. So the result of this procedure is just a shift of the Brownian motion by some deterministic function, which is, by the way, the only restriction we need is that its derivative is in L2. So this is the Sobolev class whatever h1, w21, w12, depends on the notation you prefer, so I'm not going to use any on the blackboard. So this is in the Sobolev space w21. Okay. So what is the conclusion here? The conclusion is that we know that what? That bt plus ht is a Brownian motion with respect to the measure. And what is the measure? What is the density? The density is here. So B is deterministic function, so everything here is deterministic. With respect to the probability measure, given by exponential h, no. Sorry, not exactly everything is deterministic, so still this is stochastic integral. So this is gs dbs minus 1/2 j squared dbs. Okay. In a formal way, this can be rewritten as follows. For any function on trajectories, any continuous bounded function on trajectories, or just measurable bounded, we know, let me put it in another color, so we know that the expectation of this phi computed on, let it be beta t plus ht, is exactly the expectation of this phi, of this phi computed on bt with this additional weight. The point is that, of course, it's of no importance if I put here beta t or bt. The expectations are the same. Both beta and b are the standard Brownian motion. Right? So if I wish, I could replace this by bt. This works. So this formula has a name. It's called Cameron-Martin formula. In fact, one does not need the whole machinery to establish this result, because you can notice that the result actually is not based on the notion of stochastic integral. This integral deterministic sums in dB is what I called Wiener integral. It can be defined just formally through integration by parts. So this is some statement about Gaussian measures. So one does not need the whole machinery to prove it. But again, this is rather useful to have it here, because it's exactly of the same shape. We shift trajectories now by something deterministic, and the result it causes is exactly the reweighting of the measure by something very, very explicit. So good. And the very last thing, which is sort of a cherry on the cake, is the third example. finish what I did. Okay, yeah, I'm sorry for this. Still, we have some traces on the other blackboard. It would be better to keep this right here. So a third example. In a sense, still, you can see it as a sort of a version of this example. So what I'm now going to do, I'm now going to play with MT, which is the stochastic integral dbs over bs. So I'm going to play with the function b equal to 1 over x. This is not very good because, okay, Brownian motion hits 0. Not very good. No, definitely not. Let me truncate. Anyway, I'm going to start this at the positive point, so erase absolutely. Okay. So still, this is a martingale. And I can define this dt, which is reweighting of my trajectories. So what's that? Yes, I just erased the most important formula. Sorry. So what I claim is that this martingale is actually given by the value of the Brownian motion itself. So remember, what was the connection? The connection was that this is x naught, small x. This one. The connection was that if I know d, then m is the stochastic integral dd over d. Right? So it was the way how one gets the martingale itself from its exponential martingale. So, okay, here is the formula. I mean, this is, you see, this is like dd over d. Okay? So, just exercise to check. And now, again, so what is now a measure? Now our measure, which I denote by q delta. Okay, this is d. Just let us think what's going on. We start our Brownian motion. Then there are two scenarios. Somewhere here there is a level delta. And here is a time t. In the first scenario, we just survive, and then it returns us some value. In the second scenario, we hit this level delta and stay there for forever. Yes, here. Okay. So what I'm saying is that the measure, I mean, in this case, this was x, and let me start from the same point, is that here we just have bt over x, and here we just have delta over x. Okay. We have such a measure. Now, let us pass to the limit as delta tends to infinity. So this produces us some measure, or some measure, which is what? This is x minus 1 bt, just by the indicator of the fact that it stays positive on zeros. So what's the idea? The idea is that here, when we had the cutoff, the density, the new measure we put, is very small. This is delta, right? So basically, we forbid these trajectories. So everybody else is reweighted by the value on the terminal point, but those poor guys who hit the zero level on the run, they're just killed. Okay. Well, and just a small remark. Similarly, one can introduce the second cutoff above. Let be positive. Let us fix a positive and consider stopping time. Let me denote it this way: delta A, which is the infimum of all, such that dt is not in delta A. And do exactly the same. It will give us some measure. Let me denote it d. Okay, maybe let me erase note here, dqa, which is now, okay, what's that? 6 minus 1 by a if we hit a before delta, which is delta if we hit delta before a, and which is still bt if we state delta. Right? So I mean, if it was another cutoff, the other color, here it was another trajectory which put there and stay for forever, then okay, this is the value a over x. So what is the purpose of doing all this? Just think on the setup, and again, delta goes to 0, so there is a mess with notation, okay, but I'm going to, to send delta to 0. So think about t being very, very large. And basically what happens is that almost all of the trajectories, they either hit A or 0. Those who hit 0, we just discard. And those who hit A, they get the same weight, the same A, right? So in a sense, we consider, just a conditional distribution of trajectories of the Brownian motion, provided they reach the yellow level first. Okay, so here is the reweighting of the trajectories. But now, what happens on the other side? So, on the other side, exactly as in the previous examples, so what I know is that bt minus the bracket with m is a local merge with respect to the new measure Sorry for the mess with these guys. What should I do? So this is a local martingale with respect to this measure. And again, the quadratic variation is the same as so I know this is a Brownian motion. And moreover, I know what is the link between B and beta and B. And I know that dB is what? I'm playing with the function 1 over x, right? So this is d beta plus dt bt. T solves A. At least up to the time, I mean, I don't really know what happens after I hit one of these levels. Up to time. So we arrived to a rather non-trivial claim. So imagine that we just pass to the limit at t to infinity. And 0 and t to infinity. So what is the claim? We have two pictures. One picture is for the Brownian motion. So this is one-dimensional Brownian motion. What happens is that we have a cutoff. Here A, here is 0. So what is our measure? Our measure, it just says, aha, if I hit 0, then I just discard the trajectory, it's 0. If I hit A, okay, I just stop there. Okay. So, conditioned on hit A before 0. Just set of trajectories. What we have on the other side? On the other side, we have three-dimensional Bessel process. Started from the same x. Remember, it never hits 0. I mean, three-dimensional process, okay, it stays positive until it hits level A. And what we just proved is that these two pictures are the same. So this is a slightly more involved application of Girsanov's transform, but in fact, not at all more involved. I mean, the formal computations are all done on this blackboard. So remember, this is the most important formula. So it was a Brownian motion B, then we introduced another Brownian motion beta, and then it happened that the first solved some SD with respect to the second. This is exactly what happened here, though the function was very special. And the result on the left-hand side was just this condition. Well, look, it's rather non-trivial because three-dimensional Bessel process is a very simple object. You just run simple random walks in 3D, you take modulus. Okay, that's, I mean, you do not need to know what stochastic differential equations are to define this process, right? The only thing you need is just to be able to define the Brownian motion itself. So here is again, everything is defined in terms of the Brownian motion itself, and there is this non-trivial coincidence of distributions. Okay. In particular, I don't know any discrete intuition behind of that. There are several computations how you can prove this result. But this is a sort of an example when in continuum you really have more identities, more symmetries, and much somehow nicer and workable structure than in discrete. I mean, like with the usual integration, for instance. You can do some tricks in continuum that just do not have any analogy in discrete. Okay, so that's it. What is the bottom line for the second half of today's lecture? Probably the most important conclusion is here. That when you think about such SDs, this is equivalent to introducing a new probability measure exactly on the same set of trajectories. That's what Girsanov's transform tells us. And that's of importance. Then there are some examples. Okay, here is a general scheme how to get solutions to these SDs. And then there are two applications. This application is for deterministic shifts. When you ask, okay, if I had the trajectory of a Brownian motion, and then I added some deterministic function from the Sobolev space, what happened? Okay, if it was from the correct Sobolev space, nothing. The set of trajectories is exactly the same. And the second application is this curious identity for the Bessel process. Okay, that's it.
Excuse me, are there any issues concerning passing to the limit with like t going to infinity or infinity?
Nope, not that much. I mean, the story is that, okay, if you stop this at time t, you might have different measures on the part of trajectories which survives until this time. But this is, vanishing part. I mean, so you just don't care what happens with all these trajectories. So here there is no issues. Even here there are no issues. There are some issues. It's tempting then to pass to the limit when A tends to infinity at the end of the day. And say, okay, on the left we condition Brownian motion on some zero probability event that it stays positive for forever. And on the right we have this process. I mean, this is a bit hand-waving, what this conditioning actually means. But you can think, with a cutoff. It's just a limit of statements with a cutoff. Other questions? Well, if no, that's it for this term. As far as I understand, there is no lecture tomorrow, so enjoy holidays. Thanks for attention.